Hello, my name is Lieven Penning. I'm the founder and CEO of PlanOpsim, and it is my pleasure to present to you this seminar on optical design of metasurfaces. In this seminar, we will be looking at designs of metasurface components in various shapes using the PlanOpsim software. So let's get things started. Why would we use a metasurface in the first place? Well, if we look at conventional optics like this refractive lens that you see here cut through, you see that it is made by painstakingly aligning different optical refractive or reflective components in order to balance their aberrations. This system, although performant, is very bulky and heavy and has a lot of alignment costs associated with it, and sometimes even has to be finished by hand even today. Metasurfaces promise to enhance this performance and make it much lighter, much smaller, and much simplified, and even lead to new applications by using nanostructures that locally control the behavior of the light, then distributing these over a large wafer so that we end up at a performant optical component. And all of these metasurfaces can be created using standard lithographical techniques known from the semiconductor industry. What is PlanOpsim and its role in this? PlanOpsim's role is to make this development as easy as possible for engineers and scientists using the R&D tools we provide. That is both the design software that we have brought on the market since 2021 and the design services where we help companies and research institutes develop metasurfaces using our own tools and third-party tools. And when we want to design a metasurface, it's really important that we are able to design the full scale from the nanoscale, where we make these sub-wavelength particles that modulate and control the behavior of light, into organizing them on large components which contain millions or billions of meta-atoms, and then integrating these components, because often a single component is not enough, integrating them into systems using ray tracing tools. When we look at the design steps for designing a metasurface, there are basically 3 to 4 main steps. The first one is to analyze and design the metasurface in a system. This is typically done with several components in a macro scale size, so that needs a ray tracing simulation. The output of that ray tracing simulation is the wavefront, ideal wavefront or wavefront's behavior that we want the metasurface to have. And in this design, we already inform the ray tracing system design of the capabilities of the metasurface from the nanoscale solver. The nanoscale calculations here under meta-atom design are done using full wave calculations. Because these are sub-wavelength structures, only a complete solution to Maxwell equations will be sufficient to model them. But we cannot apply Maxwell's solver to every part of the meta-atom design because the metasurface itself is too large, and full wave Maxwell solvers are constrained in time and memory. So for that reason, once we have designed the nanostructures themselves, we go on to component design, where we use approximated methods from physical optics to be able to still design large area metasurfaces, not just design them, but then also analyze them, calculating their wavefront efficiency and so on and so forth, and interfacing that to manufacturing through PDKs and GDS files. And in this seminar, we will focus on these last 2 bits, the design of the nanostructures themselves and of the components. So a question that has to be answered first is, what is the working principle of a metasurface? Well, if we think in a very general way about any optical component, its function is to transform an incoming wavefront into a new wavefront of our choice. In this case here, we see this for a lens where a flat wavefront comes in and is formed into a circular or spherical wavefront in order to form a focusing beam after the lens. And this thinking actually applies to any optical component. So if we now use our meta-atoms to locally create the wavefront, the phase that we want, and then we can map this library of structures back to the phase front that we want, we can in principle make any type of lens or any optical component that we want. So we have full control of the wavefront. And this is particularly interesting for profiles that are hard to produce as a conventional lens, for instance, for aspheric lenses or rapidly changing arrays of lenses, just to name a few, and we will see more examples of this as we go on with the seminar. The first design question that often comes when people ask us to design meta surfaces is how to design the nanostructure itself. And there are three main mechanisms that are often used by designers to create the phase and amplitude control that we want to achieve. The first method is called the propagation phase. There is also the Pancharatnam-Berry phase or geometric phase and resonant phase. We will get into each of these types later on, but in general, propagation phase works by controlling the way light accumulates phase throughout an effective medium, whereas Pancharatnam-Berry phase relies on polarization conversion through a half-wave plate, and resonant phase relies on the fact that around an optical resonant phenomenon there is often a strong phase change when you encircle that resonance. So by making small perturbations around the resonance we can achieve phase control. But let's start at the beginning. We don't actually need a separate solver for each of these type of mechanisms, because they are all part of photonics. They are captured by the Maxwell equations, so any solver that solves Maxwell equations will be able to capture all three of these effects. In the PlanOpsim software we opted to implement the RCWA calculations because in our benchmark tests comparing to FDTD solutions for the same structure, it turned out that RCWA calculations are much faster compared to FDTD while yielding the same results for this type of structures. This is particularly true for the nanostructures. It is not generally true for all types of optical calculations, but it is for the meta-atoms that we are of interested in here. When we design, there's a few other things we also need to keep in mind. The first one is, why do we use such a small structure at all? Why does it have to be sub-wavelength? Well, that has to do with the fact that if we take these tiny structures and we start to place them and repeat them periodically, this will cause diffraction. And this diffraction, where the light ends up by diffraction, is ruled by the well-known Bragg law of diffraction. So we have the incident light coming in here, and then light both in transmission and reflection is diffracted into different directions, which are all linked by a modification by a discrete number of the grating vector. And this grating vector here has the term of the periodicity below the fraction sign. So that means if we make this p small enough, we can make the grating vector large enough so that any diffraction is not allowed. It is not a propagate. The diffracted waves are not propagating, but evanescent. If we then do a bit of math on this, we can derive from this a criterion based on the refractive index of the two mediums, so the incoming and the exiting medium, and the incidence angle, and we see that if the period is small enough, we no longer have any diffraction. And as a good rule of thumb, we can say for normal incidence, the periodicity has to be smaller than the wavelength divided by the refractive index. So this is the reason that we go sub-wavelength in these designs. And then we use these structures to sample the phase in a meta-surface. And there are two aspects that we need to cover during our design phase. The first one is the spatial sampling part. So as we reproduce a lens, we don't do so by continuous phases, but by discrete phases. So that means we actually have to sample the lens finely enough. Well, how fine? We know this from signal theory by the Nyquist theorem, we need at least 2 samples per period. So that means we need 2 meta-atoms within a single spatial frequency. So this higher spatial frequency means larger angles. So it means making a short focal length or high numerical aperture lens will be more difficult, need finer sampling, and that making a large deflection angle in beam steering will also be more difficult. There's a second aspect of phase sampling that we need to take into account. In an ideal case, we would be able to have an infinitely fine reproduction of the phase curve, when in reality, when we are fabricating, we are using a finite number of elements, so we are doing a discrete stepping of the phase, and that causes a phase sampling, and this needs to be fine enough so that we have an accurate representation of the metasurface phase that we want. As a rule of thumb there, you can apply this Maréchal criterion, which says that the root mean square error should be below a wavelength over 14 to have a wavefront that is indistinguishable from an ideal one. So let's try and make these phases now. The first and most useful, most often used method is called the propagation phase, and this works by creating an effective medium. So we create a structure that is sufficiently smaller than the wavelength so that its refractive indices mix up. Some people consider this also as a picture of waveguides. In the end, it rolls out of your Maxwell solver, so it's more a matter of how you want to view these physical mechanisms rather than an actual difference. And this effective index that we create, of course, has a value between the core material that we see here and the gap material, usually air. So the tuning range, the amount of control we have, is directly determined by the index contrast that we get. And for this reason, you will often see metasurface designs using high index materials surrounded by low index materials. A typical case would be silicon or titanium dioxide surrounded by air or some low refractive index encapsulant. And this principle can be used for pillars, like you see often, but also for holes through something known as the Babinet principle. So if we can create an effective medium using a pillar, we can also create an effective medium using a void, a hole in that medium. So that's a propagation phase. Let's now see, can we use this to make phase control? And for this, I do a simple test here. You can do many others, but this is just an example. We make a structure here made out of fused silica on a unit cell of 400 by 400 nanometer, and we use our RCWA solver to simulate the radius and the phase and transmission of this structure versus the radius, which you see here as the color scale in this plot. And indeed, if we change the radius from 80 to 200 nanometer here, we see a gradual phase change from 50 down to 180 degrees and back up, so that we cover the entire range from minus 180 to 180 degrees. So we can, by carefully placing these structures, create any phase that we want to achieve. If we think of this in the waveguide viewpoint, we can just think of the core index of this waveguide having a certain effective index of the waveguide, and then as light travels through this waveguide, we accumulate the phase. And indeed, we can also see this if we do a simulation of the radius versus the thickness. We see the typical interference fringes in the transmission and reflection curves, and we can actually extract from that an effective refractive index out of the pillar's size. That was propagation phase. The second method to generate the phase control that we want was called structural birefringence, and this starts from the same principle as a propagation phase meta-atom, but now takes it a step further by breaking up the symmetry. In a symmetric, 90-degree symmetric design, the TE and TM polarizations will experience the same changes because of symmetry of the problem. But when we make a non-symmetric structure, for instance this cross shape that is longer in the horizontal direction than in the vertical direction, at that time the material will have a different response to TE and TM polarization, as you can see here in this phase plot below, where we plot the phase in TE and TM versus the length of this X and Y arm, and we see that the TE light, the TE phase corresponds strongly to the vertical direction, whereas the TM phase strongly correlates to the horizontal direction. So what we have created here is also known as structural birefringence. So in this way we can create any type of optical retardance by the index contrast that we want. And this can be used then to make, for instance, half-wave plates. If we do that, we make our nanostructure structurally birefringent, and we make it tall enough so that we have a half-wave plate, so 180 degree retardance, and we calculate its response using Jones calculus. We see that if we send in left circular polarized light, it becomes converted to right circular polarized light, and the other way around. But if we now rotate this structure, it remains a half-wave plate, but something funny happens to the phase of the output converted light here. For left circular polarized light, this gets an additional phase component of 2 times the rotation angle, whereas the right circular polarization also gets an extra phase angle of -2 times the angle. So this means by rotating the structure, we can create any phase we want for the converted polarization, as you see also here below in this simulation. So as we rotate over the x-axis, the phase changes twice as fast here below. And this allows us to create an elegant mechanism for controlling the polarization, with an important side remark that this is a polarization selective component, but it does not control the polarization, because when we set the polarization for left circular polarized light, we automatically set it to the opposite sign for right-handed circular polarized light. And in the rest of the seminar, we will use these two mechanisms to create a couple of examples of metasurfaces, but you can apply these techniques to any type of metasurface design that you want. And to get started, we'll just make a simple reference metalens that has been done also by many authors in the literature using the Pancharatnam barrier geometric phase mechanism that I just explained. So in this case, we are designing a rectangular shape here made of titanium dioxide in a unit cell size here with the parameters given here. The first thing we want to do is optimize the structure so that it acts as a half-wave plate with a high polarization conversion efficiency. And we've done that here. You see a height plot of the height of the structure compared to the polarization conversion efficiency here on the right. And we see if we choose this height here around 600 nanometer, we get a near complete conversion of the polarization. We can then use this to create our phase sampling library. We first confirm that indeed when we rotate the angle here, we get the phase control with this angle of 2 theta. We see that it's not exactly the theoretical rotation. The main reason for that is that we have a square unit cell, so the structure is not completely rotationally symmetric, but all in all this effect is minor. And we can then use this to create a metasurface lens by imposing the phase profile that we want. In this case, this is the hyperbolic lens profile, which is derived theoretically to create constructing interference at the focal plane. And then we arrive at this equation here. So we stipulate that all these rays coming from different positions must arrive with the same phase at the focal point, so that we get this equation. We then reproduce our metasurface in this way. So we place the structures so that the light is retarded with the correct phase in each location according to this equation here. And then we can design the lens. We see here a reproduction of the structures. So indeed, if we look from far away, we see the concentric rings that are typical of a lens profile and also the same as in our target. If we zoom in the GDS file for fabrication, we indeed see these rotating rectangular structures. We can then go on to calculate other types of metasurfaces, for example, more special types of beam, more complicated beam shapes. And the first example I'd like to show there is called a Bessel beam. And these type of beams are known also as diffractionless beams because they have a special property. If we look at a Gaussian beam, it's well known that this has a tight beam waist, and after that the Gaussian beam opens up with a certain opening angle. The Bessel beam has a special electric field profile that is equal to a Bessel function of the first kind, so that if we look at it here, it has an overlapping region with an extended depth of focus. Can we now create such a component? Well, let's use the propagation phase in this case. So we make a library here of titanium dioxide structures optimized for high transmission here with a height of 525 nanometer and a phase retardance going from 0 to -180 and back down. So to control the phase. In this case, we are also taking into account the sidewall angle that will occur in any practical etched metasurface. We do this by using a staircase approximation in the RCWA calculation. And in the design, we take care to avoid these resonant peaks because they are often associated with sharp dips in the transmission as well. And when we have created this phase covering library, we can use this to make our Bessel beam. So if we compare the Gaussian beam, the standard beam, to the Bessel beam, as I mentioned before, the Gaussian beam has an opening angle that is inversely proportional to the width of the beam, and a Rayleigh length, the length over which the size of the beam doubles, that is proportional to the square of the width of the beam. So if we want to make a tightly focused Gaussian beam, we automatically have a strongly diverging beam afterwards. The Bessel beam, on the other hand, maintains its tight beam waist over a much longer distance. The effective, you see here a comparison of the propagation distance from the focal point for the Gaussian in the dashed lines and the Bessel beam in the solid line, and you see indeed it has a much longer propagation length in this way. In this region, the Bessel beam maintains its shape, and that makes it interesting for instance, laser processing or microscopy applications such as light sheets. But Bessel beams have been known for a long time, and there is a classical way to make them using a component known as an axicon. This is a conical optic which creates a pseudo Bessel beam. So why would we reproduce this as a metasurface? Well, if we look at the mathematics of the Bessel beam that we can create, if we want to create a tighter and tighter beam waist in the Bessel beam, we need higher and higher deflection angles. And if we use a classical refractive axicon, from a certain angle onwards, we will experience total internal reflection here in this diagram. In the metasurface, because it's a flat component, this is not the case. The deflection is created by the phase profile of the meta-atoms. So as long as we have a fine enough meta-atom sampling, we can create any opening angle that we want. And if we now make this comparison, for instance here, comparing a refractive axicon made out of BK7 glass to a metasurface, we see that the maximum angle limit for the refractive axicon that we can make is 48 degrees, whereas the metasurface that we designed with a unit cell size of 320 nanometer can go up to 60 degrees. This is not a fundamental limit, but rather a practical limit of the design that we have made here, combined with the fabrication limits that are there for our metasurface. So this is the first example. We can use metasurfaces to create classical components, but extend their capabilities beyond what was doable with classical components. But we can take this even a step further and make components that would not have been possible in classical ways, for instance, these multiplexed metasurfaces. What I mean by a multiplexed metasurface is a component that has an entirely different behavior for a different set of incident conditions that can be set also independently. For example, this could be a different functionality for a different wavelength or a different polarization, perhaps even a different angle of incidence. And there are a couple of approaches, in fact 4, in which this has been achieved. The first one is sectoring, applying different profiles to different regions of our surface. The second one is interleaving, mixing up different components with different meta-atoms with different functionalities over the whole area of the component. The third one is to build specific libraries that have a distinct and independent behavior for the different incident conditions, for instance, different wavelengths. And then finally, there's also the option to co-optimize for this behavior over the entire nanostructure behavior. In this example, we will mainly focus on the library building approach. The sectoring and interleaving approaches inherently have relatively low efficiency, which goes down further and further as we add more and more multiplexed conditions. So multiplexing 2 conditions would lead to roughly a 50% drop, whereas multiplexing over 10 conditions would lead to a 10% theoretical efficiency from a first estimate. To show this library building approach for the multiplexing, we will start by designing a color router which focuses the light from an incident beam on different locations, different subpixels of a camera, if you will, using a metasurface. So we want to design a color filter that focuses red light here and blue light there. This is an inspiration taken from this paper here. So can we recreate that using metasurface? As usual, we start by designing our metasurface library. We use these cross structures here, and we vary different parameters, the width of these crossbars and also their length. And we change these behaviors in order to achieve high transmission, as shown here on the top plot. So the blue dots are the transmission for the blue wavelength, the red dots are the transmission for the red wavelength. And then we also examine their phase behavior for the red wavelength on the x-axis and the blue wavelength on the y-axis, so that we see that indeed this library has various different structures which cover this entire phase area of phase for 360 for 630 nanometer, as well as for 450 nanometers. So any combination of phase for 450 and 630 nanometer can be made using this library of meta-atoms. So we can pick any location and find a suitably close meta-atom that reproduces it. And with this library, we can now start designing our multiplexed metasurface. So we take the library and we now define a separate lens profile for the 2 discrete wavelengths. And you see the profiles plotted here below. For the red wavelength, we use a parabolic lens profile given here, but we add an offset term here, shifting the focal point by 12.5 microns. We do the same for the red wavelength, but we shift the central focal spot in the opposite direction. So if we recreate this, you see these phase profiles are entirely different for the 2 metasurfaces. So if we, for the 2 wavelengths, so if we shine on this with blue light, we expect the focal point to be below. If we shine on it with red light, we expect the focal point to be above. So let's put that to the test. And we use our angular spectrum methods simulations here to calculate the point spread function of this metasurface when we shine on it with the 2 wavelengths. And indeed, if we shine with red light, we see here, we get here the simulation on the top with the point, the focal spot shifted up. If we shine in with blue wavelength, we see the focal spot shifted down as we expected. We can also simulate a cross section to see how the light converges, and indeed for the red light we see a nicely converging cone to the top, for blue wavelengths a converging cone to the bottom. This is color multiplexing. We can now also apply the same type of design principles to polarization multiplexing. So we take the cross structure, the structurally birefringent structure from before, and we simulate its behavior for the different vertical and horizontal lengths. And we see here on the plots on the right for both the transmission and the phase that the phase mainly depends on the length of the arm that is parallel to the electric field in that polarization. So the TM field is mostly influenced by the horizontal arm, whereas the TE field is mostly influenced by the vertical arm. So this again allows us to select structures from this and create a library that allows us to multiplex the polarization. We did do this in this case, in this example, for 1550 nanometer, but the principle can be applied to any type of wavelength. And then we create a component like here. So we give a different target for the TE phase, where we shift the focal point to the left. For the TM phase, TM polarization, we shift the focal point to the right. We simultaneously create these two wavefronts. We see here the corresponding GDS, where you see quite nicely that indeed there are these two overlaid phase profiles visible in the fabrication GDS as well. And we can then simulate the focusing beam splitter that we created in this way. On the top left, you see a simulation of the focal spot when we shine in with TE incidence. We see 45% of the incident light is focused in this spot. If we shine in with TM incident light, TM polarized light, the focal spot is here to the right, and only less than 0.1% of the light ends up in this original yellow box. If we would compare that to commercial beam splitter, we get their similar rejection ratios in the polarization. So our focusing beam splitter here has a rejection ratio of about 2000 to 1, whereas commercial beam splitters usually show around 1000 to 1 ratio. But the important point is that we are here simultaneously focusing and splitting the polarization at the same time. So this is something that in a conventional component would not be possible. It would require at least two components, whereas here we have two or more components in a single metasurface. With that, let's move on a little bit further. The multiplexing approach is of course not limited to lensing. We can also use this, for instance, in grating designs, where here a multiplexed grating is made, where the phase profile is completely opposite for two wavelengths in the C band. So for the wavelength of 1570 nanometer, we make a phase profile that is looking like this, using the structures here on the top. The result of that is that any light incident on it, this is a reflection grating, is diffracted into the -1 order. But because of the multiplexing, the phase profile for the shorter wavelength, for 1530 nanometer, is blazed in this way. So this sends the diffraction in the other direction and allows us to create a wide angle splitting grating, which sends the light split in the diffraction orders over a large range, plus 45 degrees in total in this example. We can do this in the same plane, but because we have independent phase control, it's for instance also possible to send the diffracted light for the two polarizations. In this case, this was a polarization multiplexed grating, into entirely different directions as well. So we see here, for instance, in this design, the TM polarization is sent here to this spot, whereas the TE polarization is sent to these spots, which are not in the same plane. In fact, this is also something that would be impossible to create using conventional components alone. Those were multiplexed metasurfaces. Let's now take a next step and look at holographic metasurfaces. In a holographic metasurface is an ideal case to exploit the fact that we can have complete control over the phase distribution inside a metasurface. And we know from basic optical theory that in a first approximation, the far field intensity profile is nothing but the Fourier transform of the near field profile, and the other way around. And this is a fact that's exploited by what's known as the iterative Fourier transform algorithm, or also Gerber-Saxton algorithm, to be able to take any arbitrary incident profile like this smiley here and calculate which phase profile would be needed to create a phase-only hologram that creates this projection. This algorithm roughly works as described here. So we start from the target image that we then back propagate to the plane of the meta surface. At this point we give it a unit amplitude, but just set the phase that we want from the back propagated target image. And we forward project this again using angular spectrum method to reach the phase profile here at the far field again, which will be a reconstruction but not an exact reconstruction of the target image. Then these two images are mixed up and the procedure is repeated until the solution converges close to the target image that we had. To create a hologram in this way, there are two main requirements that we try to fulfill. The first one is we want to have a fine level of phase control, ideally a continuous phase control, also known as a kinoform. And we want to have a fine spatial frequency, a fine spatial resolution in the hologram plane, because the narrower the spatial resolution given by this Nyquist criteria that we saw before, the larger the opening angle of the images that we can create. Of course, in practice, we only have access to discrete phase levels, and we also always only have access to a finite pixel size. But precisely here, the meta surface has advantages compared to the conventional methods of making this, like a spatial light modulator, which has a relatively large pixel size, or a binary grating, which only has 2 levels of phase control. And we can indeed make these meta surfaces then in this way, and this comes straight out of our software in this case. So we design the structures as before using propagation phase. We set the target image using any image of our choice. Then we apply the IFTA algorithm, and we then our partner fabricated these structures. You see an SCM image here, and then finally also a projection experiment of the hologram that was to be projected. And in this case, it had an efficiency of around 70% in a very compact system. In fact, the whole system was not much larger than my thumb. That's a single holographic image, but now we can combine this again with the techniques of multiplexing. We make a new library again, which is multiplexed for the 2 polarizations, and also we use an off-axis incidence so that we can suppress the 0 order with a beam trap. You see here the design of the library. This was done for a wavelength of 532 nanometer using titanium dioxide structures on fused silica. Here you see the library, so each dot represents a meta surface, a meta atom that was calculated. And we plot their response to TM and TE incident light. We see that we can cover various different phases with high efficiency, high transmission, as given here by the color bar. This also underlines the need to have fast simulations. This type of plots, this type of optimization contains usually several tens of thousands of structures that are calculated. So we need to be able to iterate fast to do designs in practical times. But once we have this library, we can then send in our target image, apply the IFTA, so we calculate the required phase profile. We then reproduce that phase profile using our meta atoms and calculate back what would be the wavefront error, and finally also the projected image. And this is the design. This is all still on the computer. If we then make those demonstrators here and we put them in a little setup, we see indeed that this polarization multiplexed hologram behaves as we expected. You see here in the middle the SCM picture. On the left hand side we have the setup with TE incident light, where we project this icon of a man. And on the right hand side, when we rotate the polarization to TM polarization, we see that we are projecting a car from the same component. So by switching the polarization, we switch the image, something that could not be done with a classical hologram. So with these different examples, there are many more. We could go on forever like this. I hope to have shown you that meta surfaces allow you to create components that were not possible in conventional ways. An important aspect now to bring this into practical design, of course, is design for manufacture. And also their simulation can be of enormous assistance using sensitivity and Monte Carlo analysis. So for the rest of the seminar, I'd like to show you a couple of examples there to show how this is done on a meta surface. When we design a meta surface, of course, at the first iteration of the design, usually the atoms are assumed to be perfect. But once we actually start fabricating, all kinds of fabrication errors occur. So for instance, the sidewall angle, which is usually assumed to be perfectly straight, in fact, due to the etch process, is often not having a perfectly straight sidewall angle, but instead has a cone shape instead of a cylindrical shape. Another commonly occurring effect is that the shape or the radius or the rectangle size, whatever it may be, has a different size than as it was designed initially because of different effects during the exposure in the E-beam or the photolithography or the shrinking of any imprint resist during developing. All of these effects happen. And finally, we can also have differences in the height of the evaporated film. If we, for instance, design for a nominal height of 600 nanometer, the actual film that is evaporated might be 610 or 620 nanometer in size. So the natural question is, if we want to go to high volume manufacturers, what is the effect of these parameters and how sensitive is our optical performance to these unavoidable manufacturing effects? So let's look at these effects. We start off with a nominal design. Here in this case, we're taking a target wavelength of 4 microns using a series of amorphous silicon pillars on a zinc selenide surface in a square arrangement. And we design in the way that we have done before 8 meta atoms using 360 degrees of phase coverage. We have here a height of 5.25 micron and a unit cell size of 2 microns. And we use this to design a nominal meta lens with the parameters that you see here. So the size here was 10 by 10 millimeter with a focal distance of 20 millimeter, and we used the hyperbolic phase front as a reference point. We just make this fairly standard design. So we have here a plot of the point spread function as well as the corresponding phase function. The question we are interested in here is what happens then if the parameters change from their nominal design point. And we can do this using a sensitivity analysis. So we take the nominal design and we purposefully introduce defects all over the meta surface to, for instance, here on the left, the size of the radius. The middle point here is the nominal condition, no change to any of the pillar sizes. But as we go left and right, we start to decrease or increase the size of the pillars. And we see that the transmission changes from, in this case, 76% to 72%. So there is a slight decrease there, but there is a somewhat stronger decrease here in the focusing efficiency from roughly 60% in the nominal design to 44% at the outermost cases. The threshold here for this lens design was that as long as we want everything to remain within 90% of the nominal design efficiency, a change of plus minus 15 nanometer is acceptable. We then apply the same type of sensitivity analysis to the height, and we see here changes in height are not very sensitive to this design. So the transmission again changes from 76 to 72%, where focusing efficiency drops a little bit more. The final parameter we want to look at then is the sidewall angle, and this is, as you can see already in this plot, the most critical parameter. The transmission efficiency, as we change from a perfectly straight sidewall to a slight angle of 2 degrees, stays roughly okay. It's drops from 76 to 58%, so there is a noticeable drop, but there is a very sharp drop in the focusing efficiency, which goes from 60% to 2.4. So we almost entirely lose the light we have in this meta atom. So this shows a need to control the sidewall angle very precisely in meta surface designs. A natural question that we have is, if we know the sidewall angle, can we compensate for this? And this is what we did here in this simulation. So we take the same nominal case, the same target meta surface, the same focal length and so on. If we make the nominal design with perfectly straight sidewall angles, the focusing efficiency is 60%. If we then introduce an uncompensated error, the focusing efficiency drops to 2.4%. But if we apply a redesign of our meta atom library, taking into account that the sidewall angle will not be straight, but in fact will be 88.5%, then the focusing efficiency recovers. So we are able to compensate for a known fabrication defect, and the important part is to control batch-to-batch variations in the sidewall angle. If we look in detail at the error mechanisms that are happening here, if we look at the overall wavefront shape here, so we have here the analytical profile that we want to reproduce, in blue the nominal profile, and then in dashed lines red and green the aberrated profile. From far it looks like there's no change at all, but if we zoom in, we see that the mechanism, what is occurring is that we get these local strong changes in the phase approximation, and this translates into a loss of efficiency in the focal spot. If we look actually at the shape of the spot here, blue is nominal, orange is with a 0.5 degree angle, green is with a 1 degree angle. The shape of the spot, so the MTF function, does not change, but the intensity drops considerably. And this happens through the effect of scattering into higher diffraction orders. This is the main loss mechanism in this case. Those were systematic errors. Of course, when you fabricate, there will also be non-systematic errors. Not every meta atom changes in exactly the same way. Instead, there can be random errors. Those are modeled through Monte Carlo simulation. So we have a toolbox that allows to introduce random defects in different locations and see how that affects the focusing efficiency or other performance characteristics of the meta surface. And here in this slide we see a side-by-side comparison on the left of the systematic errors and on the right of random errors. For instance, if we look at the effects caused by changing the sidewall angle, as we've just seen, a systematic change there is very dramatic and quickly causes the focusing efficiency to plummet, whereas a random error there, so different locations having slightly different angles, has a much less strong decline in the focusing efficiency. We see a similar story for modifying the radius. Modifying the radius here a little bit causes the focusing efficiency to decline, whereas the design is more tolerant to changes that are random. One of the effects we can of course also study using a Monte Carlo example is to look at the combination of different error modes at the same time. So in this plot, for instance, we compare 3 modes of errors: the change of sidewall angle, the change of radius size, and entirely removing some of the structure. And in this plot, each dot represents an ensemble of meta-atoms which was simulated with different levels of these 3 aberrations combined. And we see here in the lower left corner, these cases have a good performance still within 90% of the nominal transmission, whereas as we go further and further away from this point, we start to have more errors. And this allows us to identify again the sensitive parameters for fabrication. A plot like this contains about 25,000 metalens simulations, so it's a time-consuming calculation that would not be possible without multi-scale calculations like we employ in our designs. If you find all of this daunting, I also want to point out the fact that since 2023, there are public PDKs for metasurfaces. PDKs are called process development kits, and these are structures that are optimized for manufacturing and guaranteed by a manufacturer. So that means that as a designer, you can select structures for a given target wavelength for which the structure is already optimized and go directly to designing optical functionalities for these wavelengths, which can then be sent directly to the manufacturer as well for fabrication using a process that is already standardized. So this allows for cost-effective and rapid prototyping directly from software into manufacturing. And with this last bit, I would like to wrap up the seminar and summarize the main highlights. So we looked at the design of metasurfaces from the meta-atom scale to the component scale. Through meta-atom design, we can create various structures using the propagation and phase and structural birefringence, and use that in components to create components with unique properties that would not have been possible with refractive optics, and we can optimize them for manufacturability using techniques like PDKs, sensitivity analysis, and Monte Carlo analysis. Thank you for your attention, and please reach out to us with any questions that you may have. Thank you very much.